For the purposes of this demo, I'm going to play the role of a data scientist at a large restaurant chain tasked with helping the restaurant operators optimize their staffing schedule. To do this, we would like to forecast the hourly foot traffic for each of the restaurant stores in 200 different locations. Let's see how we can use Snowpark and the Snowpark-optimized warehouses to build an XGBoost forecasting model to help with the task at hand. The nice thing about Snowpark is that I can use my preferred language and IDE of choice and have all the processing transparently pushed down to Snowflake. Today, I'm going to work from a Jupyter notebook. As a first step, I quickly import the required libraries. Using the Snowpark API, I establish a secure connection between Snowflake and my notebook instance. Let's start by looking at the two tables I will be using. The first table has historical hourly foot traffic per store. This table also includes a feature of whether the store is located in a college town or not. I also have a store calendar info table that has broken up the date value into individual features such as day of the week, day of month, and so forth. And this table also tracks any major holidays. To create my training dataset, I use Snowpark data frames to join the two tables. I extract the date and hour from the timestamp value in the hourly traffic table and join the date value with the calendar date on the calendar info table. As I'm doing that, I also make sure to filter out records during the hours of 10 p.m. to 7 a.m. when the restaurant stores are closed, and I also replace nulls in the holiday column. I want to confirm the table is coming along together as expected. So to quickly visualize results, I use the two pandas method, but since using two pandas from an external client will bring the data into memory, I make sure to limit the records to 5. This will be the input format for XGBoost model, where we will index on the date hour field, and the rest of the columns will be the features, and hourly traffic will be the values we want to predict in the future. To run a forecast using XGBoost, I need to provide not only the table of historical values, but also the future values. To do this, first I create a column that will have hourly records for the next 4 weeks, filtering out the closed hours. I then cross-join this with the store hourly traffic data such that each store has these values. Next, I want to add in the calendar features for the next 4 weeks. While I do this, I also make sure to replace nulls for the holiday column. I join the future store info and calendar info data frames to get our final future table. And since I don't know what the foot traffic is in the future, I filled out the columns with zeros, which will be replaced with predictions once we run our forecast. As the last data prep step, I bring the historic and future tables together. With that, I now have our final features table that is ready to run a 4-week forecast. The business objective here is to provide a store-level forecast across the restaurant's 200 locations, which means we need to run 200 individual forecasts. You might have seen some of our previous summit demos where we've showed model training using the stored procedure and the Snowpark-optimized warehouses. This is a great approach for training one model on large data. But for 200 stores, if we were to use a stored procedure, we would likely need to do a loop. And also taking into account that stored procedures run only on a single node, we would probably be better off using a UDTF for this scenario. By leveraging a UDTF and partitioning on the store ID, we're able to distribute the processing across multiple nodes and train our 200 models in parallel. Let me show you how to do this. Here, I just defined the output schema for the UDTF. You can see that only 2 third-party packages are needed, which are the XGBoost and Pandas. To first develop and test this code locally before deploying it as a UDTF to Snowflake, all I had to do was make sure I pointed my local Conda installation to the Snowflake channel, which ensures that I'm using the same packages and versions available on the server side in Snowflake. Here, I register my UDTF using the decorator and specify various required parameters such as the output and input types, name of the UDTF, required packages, and so forth. Because the same packages and versions are pre-installed in Snowflake, Snowpark automatically picks up and resolves these dependencies on the server side using the integrated Conda package manager, ensuring all my code runs seamlessly inside Snowflake. As part of our UDTF forecast handler class, I implement the standard init, process, and end partition methods that are expected by Snowflake. To give you a high-level overview, the init method initializes the processing of input partitions. The process method is invoked for each input row, and the end partition method is invoked to finalize the processing of input partitions. Next, here I set the datetime column as my index. Since XGBoost expects all inputs as numerical values, we need to convert our features to the model expected format. To do this, I convert all features to categorical type and use the pandas getDummies method to do the conversion. I then split my data into train and forecast and pass the training data to the XGBoost regressive model and the forecast data to the predict method. And finally, I iterate through the predictions and return the output, the date, hour, and prediction, which is the forecasted foot traffic per store. Now that I've finished developing my training code to get my predictions without moving any data out of Snowflake, all I need to do is call the UDTF and pass in the feature tables, which contains our historical and future data we created earlier. The UDTF runs the training on the historical data and returns the forecast for the hourly traffic. So far, all my data preparation steps, I was using a standard warehouse. Since we're training 200 models using a total of 50 million rows, where each subpartition or store ID is processing more than 250,000 rows, using a Snowpark-optimized warehouse, which comes with a lot more memory, is suited for this scenario. Before running this UDTF, I'm going to switch to a new Snowpark-optimized warehouse. There is no complexity in setting up new infrastructure or need to move data across environments. When I execute this UDTF here, it's going to take a few minutes as we're doing training across a relatively large data set. So for the interest of the demo, I went ahead and also pre-ran this UDTF. As an example, you can see this cell here, which shows the output from my previous execution. We get the hourly traffic for a future date. Now, if I go to my query history, you can see the failed run where I tried to run the UDTF using a standard 2XL. Here you can see that we ran into the UDF exhausted memory error. Here, you can see the same UDTF succeeded using the 2XL Snowpark-optimized warehouse, and we're able to train our 200 models over 50 million rows in just within 17 minutes. As UDTFs are distributed across multiple nodes, I also choose to rerun the same experiment using a 4XL Snowpark-optimized warehouse, and you can see that the model training completed in about 10 minutes. As I scroll up here, you can also see the other SQL generated from our data frame operations that during our earlier feature engineering and data preparation steps that got pushed down to Snowflake. Pretty cool, right? As a quick summary, in this demo, we saw how the combination of various Snowpark components and the now available Snowpark-optimized warehouses can drastically accelerate the speed at which you can generate ML-driven insights by leveraging the performance, elasticity, and security of the Snowflake engine, regardless of the size of your data. So before we wrap up, let's go over a few quick best practices. The nice thing about the Snowpark API is that you can use it with your IDE and development debugging tools of choice and have the execution transparently pushed down to Snowflake. So maximize that. A quick note of caution, as pointed out in the demo, is to be mindful of the use of two-pandas operation from an external client, as this brings full data into the client memory. To maximize server-side execution performance for ML tasks such as feature engineering and inference, make sure to use vectorized UDFs, which process rows in batches versus row-by-row processing of scalar UDFs. When running memory-intensive tasks such as ML training, leverage the new Snowpark-optimized warehouses. When running single model training over large data sets, we recommend using a stored procedure and using a medium Snowpark-optimized warehouse, as stored proc execution is bound to a single node. So using a larger instance will not necessarily yield additional performance gains. Consider using UDTFs to get parallelization when multiple models need to be trained on subsets of data. A good example of this is the demo we just saw where we ran concurrent time series forecasts. The last few tips are with respect to package management. We recommend using the Snowflake Conda channel for all your local development to ensure compatibility between client and the server. Build your code using the latest stable versions of third-party packages and you do not need to explicitly specify dependencies as the Conda package manager takes care of this for you. Finally, if the package you're looking to use is not available inside Snowflake, you can always submit feedback via the Snowflake Ideas board. But if the package is a pure Python package, you can also unblock yourself and bring in the package via stages. Hope you will give this functionality a try, and we cannot wait to hear your feedback and all the new cool use cases you will unlock.